Today we're going to discuss how to find the volume of solids of revolution using the washer method, which is a generalization of the disk method, as we will see. First, let's review the disk method. In the last video, we took the area under the curve, under one curve, like in 1A that we have here in front of us, bounded by the x-axis and two vertical lines, x equals A and x equals B. And we agreed that the area is just the definite integral from x equals A to x equals B of f of x dx. This is the geometric interpretation of the definite integral. And the area between two curves, just as we have in B, and notice that the intersection points are at x equals A and x equals B. Again, to get area, we were using a vertical rectangle. So let me just mark that up with a vertical rectangle. And we see that this vertical rectangle spans the region. The same is true in this diagram. A vertical rectangle spans the region. The top of the rectangle always hits the blue curve, and the bottom of the rectangle always hits the red curve. So to get the area between two curves, in terms of x, we said that the formula was top minus bottom. So this is the definite integral from A to B of f of x, which is the height of the rectangle from, okay, let's just see. F of x gives us the height of the rectangle from the blue curve to the x-axis, minus g of x, which is the height of the rectangle from the red curve to the x-axis. And when we subtract those two, we get the height of the yellow rectangle in the region. So that's why we subtract those two, and let's put brackets around this with respect to x. All right, now let's go back to 1A. When we revolve this region about the x-axis, because the rectangle is sitting on the x-axis, right, then we get what's called a disk. And if we rotate this rectangle, one of these rectangles around, we see we get a disk. And the region, even though that's not important to sketch, would be reflected down. And we would get some kind of solid. And we would sum up the volumes of these infinite number of disks. So here, the volume, when we revolve around the x-axis, would be the same limits of integration, but to represent the volume of such a disk, well, the dx is the width of the disk, which approaches 0. So the area of the circle would be pi on the outside and the radius squared. But the radius of this disk is the height of the rectangle, and that's just f of x squared. Okay. That's the disk method. But if we take a rectangle that's not sitting on the x-axis, it's above the x-axis, notice that we do not get a disk anymore. When we rotate this rectangle, there's a gap here. There's a gap here. So when we rotate the rectangle, we'll get a gap here, and it would be reflected down, right? And then the outer rim would be rotated out and around. And then the same is true for the bottom. So that this is a thickness of delta x, and this is a thickness of delta x. And then we rotate it back. So we get something like this. Behind the paper. And this is the solid piece, because that's the rectangle that's being revolved. This piece, the inside, the inner circle, is hollow, but the outer rim is solid. We call this a washer. And to get the formula for summing up the volumes of an infinite number of washers that slice through this solid, and this solid would have a hole in the middle, right? But the piece formed by these two intersecting curves, the blue and red curve, that piece, when it's rotated, forms the solid. And there would be a circular bottom and top here on the sides, right? These would be circular and these would be circular because we're revolving the whole solid around the x-axis. So the question is, how do we get the volume of such a disk? So the question now is, how do we get the volume of a washer in the kth subinterval so we could sum up the volumes of infinitely many of them? Well, let's go to the next page and take a look again. So here I have a diagram of two functions, f and g. Notice that the yellow region is the area that we're looking at, and we're bounded from x equals a to x equals b. So this is the x-axis, and this is b, and this is a. And this is our y-axis, and we're revolving around the x-axis. So here we have our typical rectangle that's in this region. So to get the area of this yellow region, we would do top minus bottom, f minus g. But when we rotate this, we've got a washer and we've got two circles. So let's look at it. So the volume of a washer would equal the area of this outer ring. And that would be the area of the outer circle minus the area of the inner circle, right? Because that inner circle's hollow. This is hollow. Would give us the area of the outer ring times the width. So to get the area of a circle, we need a radius. The radius of the outer circle is, and I will outline this in, okay, I don't know what color to use. Let's use blue. So the radius of the outer circle is this distance in blue that I'm highlighting. This is capital R. And the radius of the hollow circle, I will put in, let's see, I'll put that in green. Is that distance. The distance of the radius of the empty circle. Okay, but let's look at the outer radius. So we call this the outer radius, the capital R. So this formula would be pi times capital R squared minus pi times little r squared delta x, which is that tiny width, which will become dx when we take the limit of the number of rectangles approaching infinitely many or increasing without bound. Now the pi can be factored out. The delta x doesn't bother us, so let's see what these are in terms of our functions. Capital R, notice that the radii are always drawn toward the axis of revolution. So the axis of revolution always goes through the middle of the solid, whatever it appears. So it's all relative to the axis of revolution. So capital R, if you look at it carefully, that blue distance is the distance from a point on F to the x-axis. So this is just equal to f of x, because the distance from F to the x-axis is f of x, the y value. So capital R is f of x squared. Little r is the distance from here to the axis of revolution. So notice that that distance is always from G, it starts from G to the x-axis. And that y value is the y value for g of x. Okay, so we could say that this is g of x squared. Remember, any function is defined relative to the x-axis. So when we use f, that's a point on the curve to the x-axis. When we use g, that's a point on that curve to the x-axis, delta x. So this would be the formula for the volume of a washer in any subinterval. But when we sum up infinitely many of them, then we have that the volume revolved around the x-axis using the washer method is pi on the outside. The limits of integration are still from x equals a to x equals b, just like they are for area. But the integrand would become f of x squared minus g of x squared, and the delta x would become d of x. And remember, this is the outer radius squared minus the inner radius squared. And an easy way to remember this is that it's always the top function squared minus the bottom function squared. Almost like finding the area between two curves, except we don't square these. Instead of top minus bottom, it's top squared minus bottom squared. But that's the formula when we revolve around the x-axis. So let's summarize on the next page. So with the washer method, it is a general case of the disk method. And here we get a solid when the area between two curves is rotated about a vertical or horizontal line. But as the disk method, the rectangle must be perpendicular to the axis of revolution. So if the axis of revolution is horizontal, and the most common one is the x-axis, we use a vertical rectangle. And the formula is pi times the definite integral from x equals a to x equals b, whatever vertical lines bound the region, the area of the region, of the top function squared minus the bottom function squared. Dx, and again in terms of x. Vertical rectangles, we always integrate in terms of x. Now, let's consider when the axis of revolution is vertical. All right, so let's take a look at a diagram. So here I have a diagram where region R in diagram A is in blue. And notice that it's bounded by these two curves, and I'll outline them for you. This curve and this curve, right? Bounded by these two horizontal lines, and notice that these horizontal lines are part of the boundary of the region. And the horizontal lines are here at y equals c and d. This is y equals d, and this is y equals c. Well, to get the area of this region, we use a horizontal rectangle, because notice that a horizontal rectangle hits the right function everywhere at the same place, and the left function, the blue function, everywhere at the same place. It's like the top minus bottom on a side. And with horizontal rectangles, notice that the height of the rectangle is going across, and that's the x value at this point, right? Somehow we have to represent this distance going across, and here we have to represent each function in terms of y. So that's why we write the functions as x equals w of y and x equals v of y. Now, when we rotate this blue region about the y-axis here, notice that this horizontal rectangle that we had in the region becomes a washer, but flat washer, like a flat disc, a flat washer. And this solid is filled in here. Okay, it's filled in here. It looks like a bell, but it's hollow on the inside. The inside is hollow, and the axis of revolution goes right through the solid in the middle. So how do we represent the volume of a disc in washer in this case? Well, here we have that the volume, when we revolve around the y-axis, would still be pi on the outside. The limits of integration would still be y equals c to y equals d. But here, to represent the outer radius, well, the outer radius is the distance from the right function to the axis of revolution. So this is the outer radius. So that is w. So region R is bounded by the two curves y equals x and y equals x squared, and we want to set up an integral to find the area of this region with respect to x and with respect to y. Okay, we have to review that. And then the volume when region R is revolved around the x-axis, and the volume when the region is revolved around the y-axis. All right, again, for all of these problems, it's very important to sketch the area of the region. We do not need to sketch the solid, just the area of the region. So I sketched the parabola, it's exaggerated, and I sketched y equals x. Let's just label our axes here. And we know that the intersection points are 0, 0, and this one is 1, 1. I mean, that's easy enough to solve. Okay, now if we were to find the area of this region, and I'll just indicate where that is, bounded here. In terms of x, we must use a vertical rectangle. So I'm going to erase this. And I'm going to redraw this so I could draw my rectangles so you could see them. And here, okay. So in terms of x, we integrate with respect to x. We have a vertical rectangle. And here we know that the limits of integration are from x equals 0 to x equals 1. And the formula is top minus bottom in terms of x. So the top is the line and the bottom is the parabola. And that's our integral. If we were to integrate this with respect to y, we would have to use a horizontal rectangle. And in here the limits, the y limits of integration happen to be the same. So it's from y equals 0 to y equals 1 of the right function in terms of y, which is the square root of y, minus the left function in terms of y, which is just x equals y dy. And believe it or not, when we integrate these two, we should get the same answer because it is the same region. So that's a great exercise. But when we revolve this region about the x-axis, in order to get a washer, we must use the vertical rectangle. So when we revolve this around the x-axis, this vertical rectangle would become a washer. Okay, and again, the formula would be pi on the outside. The limits of integration are x equals 0 to x equals 1. But the outer radius is the distance from the yellow line function to the x-axis, which is just x squared, minus the distance, and the inner radius is the radius of the hollow circle. So it's here. And I'll do that in, in yellow. The outer radius is this in yellow. So we would get the actual radius, that little segment in the washer, the length of that segment. So minus the inner radius, which is the distance from the parabola to the x-axis, the green segment, which is x squared. But we have to square it, dx. Okay, now, let me just put this in black. So we square the green one, we square the yellow one, I'll put that in yellow, and that's what we have. Top squared minus bottom squared. If we rotate this about the y-axis, wrong color, the y-axis, to get the washer, we have to use a horizontal rectangle. Oops. So we have a gap here. So there'll be a gap here, and the horizontal rectangle's reflected over. So our washer would look something like this. Again, this is solid. So to represent the outer radius of this washer, again, pi, the limits of integration are the y limits, y equals 0 to y equals 1. Okay, let's just fill this in. We have to square and subtract. All right, so let's see, what do we square? So the outer radius is the distance from the red curve, the green curve to the y-axis. But we have to represent that as a function of y. And since this is y equals x squared, x equals the square root of y, but we must square it. And then the inner radius is the distance from the line to the axis of revolution, and that is just the line, y equals x. So x equals y, so we square y. Notice that this looks just like this, except we square each part. And this one looks just like that, but we square each part. So if we know how to get the area, then we automatically know how to get the volume. And that's when we revolve around the x-axis or the y-axis for the washer method. Now I'd like to show you the animation.
Okay, so now that I am on this program, I wanted to show you the disk method with Geogebra. This is a very nice animation here. So I have the y equals the square root of x, and going to rotate the region bounded by y equals the square root of x and the x-axis about the x-axis. So let's do that. And here we have 5 rectangles. So if we spin these rectangles, notice we get these discs. The disc is different from a washer because it doesn't have a hole in the middle. Okay, so that's our disc. And okay, it says disc filling. I don't know what that does. Oh, it fills in the solid so we could see it. And as we increase the number of rectangles, notice that the discs become narrower and narrower, and it fills that paraboloid looking solid. So I thought I'd show you that. Okay, so that takes care of the disc versus the washer. So I wanted to show you what the washer method looks like when we rotate the line and the parabola about the x-axis. But notice that I had to change the equation of my parabola because it was too narrow. So I made the parabola wider by multiplying x squared by 0.1. But right now, I just want to show you the picture. So here, notice that this is the area bounded by the 2 curves, the line and the parabola. And I have 5 rectangles, 1, 2, 3, 4. Well, we couldn't make the 5th one, but there are 4 rectangles. If we rotate these around the x-axis, we get the washers. And notice that each of these are washers. Okay, now the volume of this washer would approximate the volume of the solid. Now, if I just reset it, and I make this into, say, 10, if I could get 10 there. Okay, so when we rotate these washers, well, we rotate the rectangles, we get these washers. You see how they're forming? Okay, so notice that this piece at the edge is solid, but inside is hollow because there's a space between the region and the x-axis. And if I make this solid, I don't know if I can show this. No, I can't pull it now. Yeah. Move that over, we have a better
And I
picture
would
of
like
the
to
solid.
conclude by saying that the disk is a special case of the washer where the inner radius is equal to 0. And that takes care of our lesson on volumes of solids of revolution using the washer method. Have a wonderful day.